Okay, in this video, we're going to be going through proof by induction, which is this is the stuff which is more relevant to the stuff that if you went through university and you actually did proofs, you do a lot of this stuff by proof by induction. Now, first of all, let's have a look at this. Proof by induction, we're using inductive logic. There's two ways of reasoning in logic. We've got deductive reasoning. Takes general facts, produces a specific conclusion. And of course, we've looked at, so inductive reasoning takes specific facts and produces a general conclusion. This type of reasoning is most common in sciences, theory of gravity, for example, and of course, we can also use in mathematics. So we're looking at inductive logic, proof by induction. Hence, the word induction comes from inductive. Now, with induction, we have a little bit of English as well as a process which, if you follow this process, you really can't go wrong. A lot of these are quite interesting. There's also some really long, lengthy ones which we won't certainly be doing or assessed on. But the way to do induction is this. Now, if I just get my little highlighter out. The first step of induction is that we need to show that a statement is true for n equals 1. Because if it's true for n equals 1, of course, it can be true for other things, but that's the first thing we need to do. Now, we're not assuming that is true. We've got to show that that's true. Okay, and if we show that that's true, it's usually quite an easy task. Okay, so for example, let's have a look over here. I'll get my highlighter out. So something along the lines for this, for n equals 1, we can later. So what we're doing is we're sort of showing that it's true for n equals 1. Then what we're doing is we're assuming that for n equals k that it is actually true. And that is going to be, so we've done step 1, we show that it's true for n equals 1. We then show that if the statement is true for some n equals k, then it is also true for n equals k plus 1. So we're actually assuming that it's true for n equals k. But then when we prove that it's true for n equals k plus 1, that means that all cases are true. Okay, so that's the step behind it. Yes, you can use English, but a lot of the time we're using maths and it's sort of almost feels like a direct proof just broken up into stages. Then, of course, we conclude that if it's true, and this is really important with English, using English, you're going to lose marks if you're just simply doing it as a maths problem. If it's true for n equals 1, and it's also true, therefore, of course, by doing step 2, we've also shown that it's true for n equals 2, and obviously for all steps, everything else, n equals 3, 4, and 5, and 6. So if we just keep adding one step, if we've proven that it's true for n equals k plus 1, then it must be true for all cases. Okay, so it's true for all integers which are greater than or equal to 1. There are some cases where it's not true for n equals 1, but it's true for some integer, but generally speaking, we'll be looking at for all positive integers. All right, now let me talk you through this one. It says, prove that n squared minus n is even for all integers, n greater than or equal to 1. I've already got my working up here, so let's sort of talk you through this. So first of all, step one is that we have to show that for n equals 1, we substitute. Now, by the way, the textbook does it a slightly different way. Mrs. Klein might also sometimes do it a little bit a different way. Sometimes they will use like a sort of almost like a function notation. They'll say things like p of 1. Okay, I just don't. I do it a different way. It looks a bit different, but of course you can, and you can do it for that. But I like to do it. I've always done it this way. This is the way I was shown doing proofs at university and things like that. Okay, so I just, your choice, you will see slightly different notation in the textbook. All right, so for n equals 1, let's substitute that. Clearly that is 0. And of course we can see that if I factorise that, we've got an even times an odd, which is an even. Okay, so we've shown that it's true for n equals 1. Now we have to say the words, assume that it is true for n equals k. If you're using another notation, you could say p of k, all right? So it's sort of function notation. Now, what that means is so I'm substituting k in. So obviously instead of n squared minus n, it's k squared minus k. But as you can see, that that factorizes to this, and we know that this could be any number. That means that that's a definition of an even number, isn't it? Okay, so we assume that's true. So that means wherever you see that k squared minus k, or factorise k minus 1, then we know that is even. Now what we've got to do is we've got to prove that for n equals k plus 1, that, and of course, often you could see it like this, p of k plus 1, it's function notation. Let's have a look. What we do is we sub in for n, we sub in k plus 1. So n, instead of n squared, it's k plus 1 all squared. Minus n is now minus k plus 1. Now notice what we do is when we expand this out, notice we've got this, we've got over here that, well, when I simplify this, we actually have shown this one. Sometimes you need to use this fact later. But you can see here that when I expand this out, I'm going to get k squared plus k. We can just simply factorize that. This is also even. And then we need to do a concluding statement. And our concluding statement is that we've shown that for n equals 1, it is true. It is also true for, we've assumed that it's true for n equals k, and we've proven it's true for k plus 1. Therefore, it's true for all values of k. So it's quite predictable, the process you would use for this. And if you stick to these rules, you're going to be absolutely fine. Now, of course, I'm going to talk you through this second one, but then I'm going to get you to have a go, and we'll write this up on the board to finish this off. Let's have a look. First of all, you've got prove that 7 to the power of n plus 2 is a multiple of 3. We're using induction, inductive logic. So first of all, for n equals 1, that's the easy part, isn't it? Start off with that. 7 to the power of 1 plus 2, of course, is 9, which is a multiple of 3. So therefore, it's true for n equals 1. We therefore assume that it's true for n equals k. Now, this is the thing. This is why we do this a lot. Sometimes this n equals k, we need to use that later. It'll help us. In the last one, we didn't necessarily need it. But notice that 7 to the k plus 2 is a multiple of 3. We know that because we've assumed it. Okay, we've made that assumption. We've assumed that it's true. Now, when we go and show that we prove for n equals k plus 1, you can see there that I can split this up, can't I? I can split this up as 7 to the k plus 1 is 7 to the 1 times 7 to the k, and of course, plus 2. Okay? Now, you can later on see that we can then since prove that is a multiple of 3. When you prove that that's a multiple of 3, you then have shown that you've proven that it's true for n equals 1. You've proven that you've assumed that it's true for n equals k. It's also true for n equals k plus 1. Therefore, you can use your inductive logic is that it's true for all cases. Okay, now what we're going to do is, if you're watching this on YouTube, we're going to be pausing this now and would like you to have a go at it. We're going to do it in the board in class. We're going to do it up on the board, and we're going to share our solution, how we did it at the end. Let's just talk you through, we won't go for too much longer. We'll keep this video short. So let's talk you through this. When doing these, once you do a few of these proof by inductions, you can see that they start to be quite repetitive, and it's a very similar process. So you can see here for n equals 1 that 1 squared, of course, is 1, which is true. That's the easy part. You will get a mark. If this is worth 4 marks, you're probably going to get a mark just for doing that. You should never leave these blank. Even if you forgot a couple of steps, then assume that it's true for n equals k. So we know that what we're told, we're substituting k in, and we're assuming that that is true. Now what we're going to do is we're going to really keep that aside, because we're going to need to use that later, and generally that's what we'll have to do with these proof by inductions. Because when you sub in n equals k plus 1, we've subbed that into here. We get over here that we've got this, but notice that we already know what 1 plus 3 plus 5, we've already been told what that is. But so therefore what we can say is we know that that's k squared, but on the right hand side we've got k plus 1 all squared. So what we can say is that we're simply substituting that in. Now, looking at the left-hand side, how do we get, we're really just looking at that. Is this the same? Which indeed it is. So we've got k squared plus 2k plus 1 is indeed the right-hand side. So therefore, it is true for n equals k plus 1. Since it is now true, and of course a concluding statement, since it's true for n equals 1, n equals k plus 1, it's true for all integers. Now, I'm going to pause this and show you an exam question, a typical exam style question. Let's see if we can do another induction and give that a go. All right, so we've looked at the 2018 exam. Here we go, worth 4 marks, 10% of your paper. Proved by mathematical induction, this one. If you're watching this, have a go. My class, we're going to have a go at it now. All right, so here's Ricky from our class. Here's how he has done it. And as you can see, that this will be good for full marks. He has assumed, he's shown that it's true for n equals 1. I'd like to probably say which is true. You say it's true for n equals 1, but that's okay. He has then assumed that it's true for n. So assume that n equals k is true would be what I would do there. And so that means that this expression here, 1 to k squared, that is true. So so he has written it down here. We can see there that we know that if I go up to the k squared is going to be equal to k plus 1, 2k plus 1 over 6. Now, of course, you could expand all of that out and show the left-hand side is equal to right-hand side. And for some of these, you absolutely need to. But so I guess a lot of the time, sometimes you're going to be able to factorize and do it with less steps. You can see, though, that because that is k plus 1, 2k plus 1, that if you were to obviously do this over 6, and take out k plus 1 all squared, you should be able to get to this. Show that the left-hand side is the right-hand side. It's true for n equals 1 equals k, n equals k plus 1. Therefore, we can say it's true for all values of n. Okay. There you go. That's induction. One thing I won't go through it yet, but again, if you wanted to try this now, if you're watching this again, I'm going to find another exam that we'll go through. Just once you go through these, they start becoming quite familiar, all right? And then some of them are quite a fair bit of fun. Here's a very similar one from another exam, exam 2. This is 1 times 2, 2 times 3. By all means, if you want to have a go at this, feel free to have a go. You could look up a lot of these mathematical inductions. You can Google a lot of them and find the solution. All right.